Imagine your car for a second. You're driving down the highway, and suddenly the check engine light pops on.
Oh, yeah, the dreaded light.
Right. It's a warning system, but it usually only turns on when something has already gone wrong, like a belt has snapped or you're just entirely out of oil.
Right, it's too late at that point.
Exactly. Now imagine if you had a check engine light for your own body, but instead of warning you after the engine breaks down, it actually analyzes the micro vibrations of the engine and warns you hours before a critical failure even happens.
That is the difference between a reactive system and a truly predictive one.
Yeah.
And in medicine, crossing that threshold from, reacting to an emergency to predicting it before it happens, it's quite literally a matter of life and death.
Okay, let's unpack this. Because today, our mission for this deep dive is to explore a really remarkable patent. It's for an AI-enabled portable device for continuous patient monitoring.
And this isn't just like a minor upgrade to existing hospital tech.
No, not at all.
It's a fundamental shift in how we monitor human health.
Yeah, and we should mention the team behind it. The inventor is Dr. Gandhi Bhaskar Pathrudulanka,
Right.
and the applicant bringing this forward is NIMS University Rajasthan Jaipur. Plus, the patent agent is Narendra Vikram Singh, identified as ENPA 2436.
It's a massive, truly comprehensive piece of intellectual property.
It really is.
But to genuinely grasp what Dr. Lanka and the team at NIMS University have built, we first have to understand the chaotic reality of modern medicine that made this invention so desperately necessary in the first place.
Right, because current medical monitors, they're essentially like a smoke detector that only goes off when the entire house is already engulfed in flames.
That's a great way to put it.
Yeah, they just completely lack foresight. Like if you walk into an intensive care unit today, you are surrounded by incredibly expensive screens. But as advanced as they look, they are overwhelmingly static. They only beep when a patient's vital signs have already crossed a life-threatening threshold.
And the data in a standard ICU is also severely fragmented.
Oh, right, it's everywhere.
Exactly. You have multiple independent devices continuously generating data. So there's one machine dedicated to heart rate, a separate one for oxygen saturation, another one for blood pressure.
They don't talk to each other.
No, they operate in complete isolation.
Right.
Because these machines don't talk to each other, the clinicians are forced to act as the integrators.
Wow.
They have to manually interpret all this disjointed data. Like they're cross-referencing a drop in oxygen on one screen with a spike in heart rate on a completely different screen.
Which just sounds like a recipe for mistakes.
Anytime humans are required to manually compile and, analyze complex, high-stakes data under immense pressure, human error isn't just possible, it is inevitable.
We also have to talk about the psychological toll of this setup, right? Like alarm fatigue.
Oh, absolutely.
Hospitals are just an endless symphony of beeps. And because these traditional machines only trigger when a strict numerical threshold is crossed, they go off constantly for really minor, non-critical fluctuations.
Right, exactly.
A patient shifts their weight in bed, a sensor momentarily loses contact, and an alarm just blares.
And if everything is beeping all the time, nothing is an emergency.
Yeah.
Alarm fatigue causes clinicians to subconsciously tune out the warnings, which unfortunately delays critical interventions.
Right.
Now, people have tried to solve this before. The patent actually references specific prior art that attempted to move the needle.
Okay, like what?
Well, there's a Chinese patent, CN 204169837U, which outlines a portable device that captures patient parameters and then sends them to a remote expert system for treatment recommendations.
But sending data to a remote system still sounds highly manual and, well, delayed.
Right.
The intelligence isn't right there at the bedside.
Exactly. And there's also a European patent, EP 3847667A1.
Got it.
And that one focuses on artificial intelligence to monitor health data from wearable devices. But these prior systems, they lack real-time, highly integrated predictive analytics happening locally.
Ah, I see.
They just don't solve the core issue of anticipating deterioration from really subtle overlapping trends across multiple physiological signals simultaneously.
Right. So to make this predictive leap, Dr. Lanka's device first needs to gather a flawless picture of the patient. It completely redesigns the flow of physiological data.
It really does.
It starts with an integrated sensing hub. This is module 101 that captures an incredibly wide array of signals. So you have ECG for the electrical activity of the heart, EEG for brain waves, pulse oximetry for blood oxygen or SpO2,
Hmm.
plus non-invasive blood pressure, core body temperature, and respiratory rate.
That's a lot of data.
It is.
Yep.
But it doesn't just passively collect this data. The sensors actually include self-calibration and impedance checking right at the source.
Oh,
Yeah, so it ensures the physical connection to the patient is optimal before the data even moves downstream.
which is huge.
Yep.
And that pristine data collection leads into the processing phase. This is handled by Module 102, a high-performance ARM Cortex-M7 microcontroller.
Okay, an ARM processor.
Yeah, and it runs a real-time operating system, specifically free RTOS.
Right.
In a medical device, a real-time operating system is just non-negotiable because it guarantees deterministic, immediate task execution. There is no lagging, there are no background updates slowing down the processor.
But how does it handle the sheer volume of noise in that data? I mean, an ICU isn't a controlled lab environment. Patients are coughing, they're moving, nurses are adjusting cables.
What's fascinating here is how the central processing unit acts as a highly selective bouncer for the artificial intelligence.
A bouncer, I like that.
Yeah. Before the AI even sees a single data point, the processor scrubs the raw signals using advanced mathematical techniques. It uses wavelet decomposition.
Which does what, exactly?
It essentially takes a complex signal and breaks it down into different frequencies. Think of it like taking the sound of a full orchestra and mathematically isolating just the flute.
Oh, okay. So it can isolate the true frequency of a heartbeat from the chaotic frequency of a patient shivering, for example.
Precisely that. It also uses adaptive filtering,
Okay.
which functions a lot like active noise cancellation in your headphones. It identifies the ambient electrical noise or motion artifacts and actively subtracts them from the signal.
That makes a lot of sense.
And finally, it uses moving average smoothing to eliminate sudden, meaningless spikes. So by the time the data reaches the AI, it is perfectly clean, normalized intelligence.
And the AI, Module 103, is the actual brain of this operation.
Hmm.
And it doesn't rely on simple logic rules.
Not at all.
It utilizes heavy-duty deep learning. Specifically, it combines convolutional neural networks, or CNNs, with recurrent neural networks utilizing long short-term memory, or LSTM layers.
Right.
Running these kinds of models in real time at the edge is just a massive computational feat.
It really is.
Yeah.
And we should break down why it requires both of those specific architectures.
Sure.
Convolutional neural networks, the CNNs, they are brilliant at spatial pattern recognition. They are typically used in image processing.
Right, like facial recognition or something.
Exactly. But in this context, the CNN is looking at the literal physical shape of an ECG or EEG waveform.
Oh, wow.
It's trying to spot structural anomalies in the peaks and valleys of the signal itself.
So it's acting as the visual diagnostician looking at the geometry of the heartbeat.
Yes. Then the long short-term memory layers take over for temporal sequence prediction. The LSTM analyzes how those geometric shapes are changing over time.
Okay.
So it might notice that a waveform is widening by just 2% every hour,
Which a human would never catch.
a trend completely invisible to the naked human eye. And by cross-referencing that subtle trend with a slow drop in blood pressure, the LSTM can forecast a hypotensive crash hours before the patient actually goes into shock.
Okay, but my immediate concern here is, just trusting a black box algorithm with a patient's life. Like, how does this system account for the fact that a healthy pediatric patient and an 80-year-old cardiac patient have completely different physiological baselines?
That's the big question.
Right, because a heart rate that signals a crisis for one might just be the daily normal for the other.
And that lack of context is the exact vulnerability that plagues most AI systems in healthcare today.
Yeah.
But to solve this, the patent introduces Module 110, a dedicated clinical customization protocol.
Mm.
It dynamically adapts the AI's decision boundaries based on specific patient profiles.
How does that work in practice?
You input the patient's age, their known comorbidities, and their medication history, and the system literally shifts its mathematical baseline.
Oh, so it effectively shrinks or expands the warning thresholds based on who is actually in the bed.
Exactly. And it goes even further through feedback-based learning. The system monitors how clinicians react to its alerts. If it flags a specific heart rhythm and the doctor dismisses it as normal for that specific patient, the system recalibrates. It learns what a true positive is for the individual, continuously refining its own model so it stops crying wolf.
Wow. And context seems to be a really major theme of this patent, extending beyond just the patient's medical history to their literal physical surroundings. Right?
Absolutely.
The device incorporates an environmental context module that detects ambient temperature, humidity, barometric pressure, and even geolocation.
Yeah.
And I initially wondered why a medical monitor needs to act like a weather station.
Well, imagine this portable device is deployed in a pre-hospital environment.
Okay.
It might be in the back of a speeding ambulance or a military triage tent in the middle of a desert. The AI needs to distinguish between environmental changes and clinical deterioration.
Oh, right, because if the ambient temperature in the tent spikes to 100 degrees, the patient's skin temperature and heart rate will naturally elevate.
Exactly. The environmental context allows the system to recognize that the patient isn't necessarily developing a dangerous fever. They're just in a sweltering room.
That is so
It
smart.
factors the barometric pressure and ambient heat into its calculations. So it prevents a cascade of false alarms simply because the environment changed.
Okay, so when the AI filters out all that noise, adjusts for the patient's history, checks the environmental context, and finally predicts a legitimate impending clinical event, how does it actually communicate that without adding to the noise of the hospital?
Right, through Module 104, the Intelligent Alert Management System, it categorizes the predicted events into critical, high, medium, or low severity.
Okay.
And it utilizes visual cues, audio tones, haptic feedback, and remote notifications to the nursing station.
But the crucial element here is the intelligent deduplication logic, right?
Yes.
Because if the AI predicts a respiratory failure, the heart rate sensor, the oxygen sensor, and the respiratory sensor are all going to show alarming data simultaneously.
All at the same time.
But instead of blasting the clinician with 3 separate overlapping alarms for the same underlying event, it consolidates them. It delivers one clear contextual warning.
And all of this intelligence is delivered via Module 105, a dynamic touchscreen dashboard.
Nice.
But in a medical setting, a touchscreen isn't always practical. The patent specifically details that the interface supports robust gesture and voice control.
Oh, that solves a massive interface issue, because if a surgeon is scrubbed in or an EMT is working in a really messy trauma situation, they can't break sterility to tap a screen or acknowledge an alert.
Exactly.
They can just wave a hand or use a voice command to silence an alarm or request a different data view.
Yeah, it's brilliant. And while the local interface is handling the immediate room, Module 106 is heavily focused on secure wireless communication with a broader hospital network.
Which is vital.
It's equipped with WPA2 Wi-Fi, Bluetooth Low Energy, cellular LTE or 5G, and even satellite communication capabilities.
Wow, satellite too.
And all of the data is wrapped in TLS and AES encryption, fully compliant with stringent medical privacy standards like IPA and GDPR.
The sheer redundancy of those communication protocols is fascinating. If a rural clinic's Wi-Fi goes down during a severe storm, the device doesn't lose its connection to the remote specialist. It just instantly pivots to cellular or satellite.
Right.
But transmitting continuous high-fidelity deep learning data over a satellite connection sounds like an absolute bandwidth nightmare.
It would be, but that is where a specific telemedicine mode outlined in the patent becomes so vital. The device is smart enough to understand the limitations of its own network connection.
Okay.
If it detects terrible bandwidth, it dynamically shifts its transmission strategy.
So instead of trying to push a heavy, continuous stream of raw ECG waveforms, which would just bottleneck and fail entirely, it compresses the communication.
Yes.
It prioritizes transmitting the critical alerts and the AI's clinical summaries. Like, it sends a tiny data packet saying 98% probability of hypotension in 2 hours rather than gigabytes of raw sensor data.
Exactly. It intelligently saves bandwidth, so the life-saving insight always makes it out of the room.
That is just a profoundly pragmatic approach to edge computing.
It really is.
Yeah.
But, running continuous real-time operating systems, processing wavelet decompositions, and maintaining satellite uplinks requires significant infrastructure. A portable device this powerful is completely useless if its battery dies halfway through an ambulance transport.
Right, which brings us to Module 107, the Power Management Unit, which addresses that heavy load. It features a rechargeable lithium polymer battery engineered to last a full 24-hour cycle of continuous monitoring.
Right.
But it also incorporates sophisticated power optimization logic to really stretch that battery life if the network drops or sensors are detached.
And the detail that really caught my eye here is its support for alternative power sources. The Power Management Unit is designed to interface with solar or kinetic standby sources for off-grid operations.
Which means this device can function indefinitely in a disaster relief scenario following an earthquake, or in a deep rural clinic that only has intermittent access to a reliable electrical grid.
Exactly. And all that process data needs a safe home, right?
Yeah.
Module 108 handle local data storage. It utilizes AES 256 encryption. But more importantly, it uses a hierarchical storage method.
What does that mean exactly?
Well, if the internal memory starts getting full during a prolonged off-grid deployment, it doesn't just randomly delete old files. It retains the highest urgency critical event data and purges the baseline normal physiological data first.
Oh, that makes perfect sense. And tying all this hardware together is Module 109, a modular software architecture built right on that real-time operating system.
Right.
And the modularity allows for over-the-air, or OTA, updates. Hospital IT departments can push firmware patches, updated AI models, or new multi-language packs to the device seamlessly without ever having to take the monitor offline or interrupt active patient care.
Which is a huge time saver. And the physical chassis holding all this technology is engineered from a medical-grade polymer. It is specifically built to withstand the repeated, highly corrosive chemical sterilization cycles that hospital equipment must endure daily.
Yeah, it has to be tough. We also have to consider the scale of a hospital. A single device is great, but an ICU is monitoring dozens of patients simultaneously.
Right.
So the patent includes a multi-patient monitoring architecture that uses virtual local area networks, or VLANs. This securely isolates and manages parallel data streams from multiple patients on a single hospital network, ensuring there is absolutely zero cross-contamination of patient data.
Exactly. So we've spent considerable time unpacking the mechanics of the AI, the
Okay.
edge computing, the hardware redundancy. But the true test of any medical invention is how it actually changes a doctor's reality on the floor during a 24-hour shift.
Yeah, and the patent visualizes this real-world application beautifully in its methodology section, Method 200, essentially outlining an automated pipeline. It continuously acquires the physiological data in step 201, pre-processes it to remove the noise in 202, feeds it into the AI for analysis in 203, categorizes the alerts in 204, displays the insights in 205, securely transmits the data in 207, and constantly adapts its own baselines in step 208.
And that pipeline culminates in a feature that will likely become a clinician's best friend. This is step 206, the automated generation of daily clinical summaries.
Oh, this part is amazing.
Traditionally, a doctor preparing for morning rounds spends hours hunting through fragmented charts, staring at raw data trends, and just trying to mentally construct a narrative of the patient's last 24 hours.
It's exhausting just thinking about it. But this device takes on that entire administrative burden. It automatically compiles comprehensive 24-hour trend reports. It builds the graphs, formats the tables, and highlights the AI-generated predictive insights, presenting a cohesive narrative of the patient's trajectory.
And it doesn't just display that narrative on a screen. The system integrates a text-to-speech engine, specifically noting the use of the open-source Mozilla TTS framework to convert these complex daily summaries into fluid, human-quality audio presentations.
So what does this all mean? It's effectively like having an automated, highly trained medical intern meticulously preparing your morning briefing and turning it into a mini audiobook.
Yes.
A doctor can literally listen to a highly detailed AI-synthesized summary of a patient's overnight vitals while they are scrubbing their hands, prepping a sterile field, or walking down the hallway to the patient's room.
It fundamentally reshapes the medical workflow.
Yeah.
By reclaiming those lost hours of administrative data gathering, the clinician can spend their limited time actually making critical decisions and interacting with the patient, armed with perfectly organized intelligence.
Looking at the legal foundation of Dr. Lanka's invention, the patent sets forth 10 specific claims that lock in this intellectual property. These claims legally protect the unique integration of those convolutional and recurrent neural networks at the edge. Right.
The multimodal intelligent alerting system, the gesture-based interface for sterile environments, the VLAN multi-patient scaling, and that automated text-to-speech summary generation.
And by securing those specific methodologies, NIMS University is positioning this device to have a massive global footprint. The patent explicitly aligns this technology with the United Nations Sustainable Development Goals, which highlights its intended impact beyond just wealthy urban hospitals.
Yeah, it targets SDG 3, good health and well-being, by shifting care from reactive to proactive. It advances SDG 9, industry, innovation, and infrastructure by pushing the boundaries of edge computing and medical devices. But the most compelling alignment is with SDG 10, reduced inequalities.
If we connect this to the bigger picture, That is perhaps the most profound aspect of this entire deep dive.
Yeah.
Today, the highest quality of predictive, continuously monitored care is restricted to elite, well-funded intensive care units in major cities. Right. But by taking all of this heavy AI processing, combining it with telemedicine bandwidth-saving protocols, and backing it up with solar power capabilities all inside a portable polymer chassis, this technology effectively democratizes elite medical care.
It really does. It takes the combined analytical expertise of a dozen cardiac and respiratory specialists, crystallizes it into software, and embeds it into a box that can sit next to a bed in a rural clinic, a remote field operation, or a developing nation where specialized personnel are simply not available.
It transforms healthcare from a reactive scramble, waiting for that traditional smoke detector to go off, into a proactive, continuously learning science focused on preventing the fire from ever starting in the first place.
It is a profound philosophical shift for modern medicine.
It really is. I want to leave you with a final thought to mull over today as we wrap up our deep dive into Dr. Lanka's work.
Okay.
We have been exploring a highly advanced edge computing device designed for high-stakes hospital and field use. But technology always follows the same trajectory. It always shrinks, and it always gets cheaper.
Oh, that's true.
If this artificial intelligence can predict a clinical event hours before it happens using convolutional and recurrent neural networks in a portable hospital monitor, how long until these exact predictive models are embedded in the consumer smartwatch currently sitting on your wrist, predicting a health crisis before you even feel a single symptom?
Wow. It is not a matter of if, but when.
Exactly. Until next time, keep diving deep.